This is the solution for problem D2.92, and in this problem we have a first order high pass filter using an op amp. So we have our input voltage here and our output voltage here. We have the op amp, so it's an inverting amplifier, right? But because we have this capacitor here, it implements a high pass filter. Okay, so from this circuit here we need to figure out what's the voltage transfer function. Okay, and we can redraw this, we can call this one here actually as Z1, so our impedance Z1, and this one here our impedance Z2, and then we know that the transfer function V out over Vi is equals to minus Z2 over Z1, right? The same as an inverting amplifier, but now using impedances. Okay, this is the analysis in the frequency domain. It simplifies the analysis of the circuit. So we can write Z1 as R1 plus 1 over J omega C, and Z2 equals to R2, right? So if we substitute Z1 and Z2 in this equation up here, the voltage transfer function that we get, H of J omega, which is the same as V out over Vi in the frequency domain, is equals to minus Z2, so it's R1 plus 1 over J omega C divided by, oh sorry, it's not, this is Z1, so it's Z2 first. So it's Z2, so it's R2 divided by R1 plus 1 over J omega C. And we can simplify this equation here by isolating R2 and R1. So we isolate R2 in the numerator and R1 in the denominator. So that's just a way to simplify the equation, right? So H of J omega is equals to minus R2 over R1 times 1 over 1 plus 1 over J omega C R1. Okay, so that's the voltage transfer function. Okay, we could simplify multiplying by J omega C CR1, but it's just a matter of rearranging the equation, like writing the equation in a different form. But this one here is the transfer function that we have. Okay, and you see later why I'm keeping this equation this way here. Okay, so that's the voltage transfer function. So this transfer function, it basically dictates what happens to the input, what happens at the output based on the frequency of our input signal. So probably if we plot the Bode plot for this transfer function here, we would see what happens to the magnitude and what happens to the phase. Okay, so basically that's the equation that dictates what's happening to the magnitude and phase our output signal based on the frequency of our inputs, frequency and amplitude of our input signal. Now part B is show that the high frequency gain is minus R2 over R1. So again, if we rewrite this voltage transfer function here, H J omega equals to minus R2 over R1 times 1 over 1 plus 1 over J omega CR1. It basically means that at high frequency, omega is equals to infinite, so a very high frequency. Now if we plug in this this omega equals to something very large, or if you want, call this one here S and this one here S, and say that S is equals to infinite, right? Basically this term here, okay, it goes to 1, because this term here goes to 0 as frequency here goes to infinite, and then we get that h of j omega is equals to minus r2 over r1. And if you want to be more precise, we can take the magnitude here, okay, and that would be r2 over r1. But the thing is that the high frequency gain is indeed minus r2 over r1. So let's not take the magnitude here, and let's keep with the minus because that's the answer, right? So this is the gain that we have, r2 over r1. And that's the solution for this part B. Okay, so this is a constant gain that we have for very high frequencies. So for large frequencies, that's the gain that we observe in this particular circuit. Now for part C is that show that the 3 dB frequency is omega naught equals to 1 over CR1. So in this part, we basically need to find out what's the frequency that our magnitude of the voltage transfer function becomes 3 dB lower than the passband of the filter. So this is the passband, right? And if we start decreasing, remember it's a high pass filter, so we allow higher frequencies to be um, shown at the output. So the output becomes our input times that high frequency gain. But if we keep decreasing the frequency, we start to decrease the gain. Okay, and if you represent the gain in dB here in the log scale, so once we decrease by 3 dB, what's the frequency that we get this from this plateau here, from this constant gain to that constant gain minus 3 dB? And why 3 dB? Because if we look at the 3 dB frequency, basically it means that our power at the output is going to be half the power of our input signal. Okay, because here we are talking about the voltage transfer function, and usually powers is proportional to the voltage squared. So if we take 1 over square root of 2, that basically means that's 0.70, and basically this is squared. So if the voltage is decreased by 1 over square root of 2, it means that power has decreased by 50%. Okay, so we need to define when does the voltage transfer function decrease by 1 over square root of 2. So when it gets to 1 over square root of 2, right? And 1 over square root of 2 of the constant gain that we have at higher frequencies. Okay, so what does it mean? It means that if we take the voltage transfer function that we had up here, so let me copy this equation here. So h of j omega is equals to minus r2 over r1 times 1 over 1 plus 1 over j omega c r1. Okay, so that's the voltage transfer function that we have. So when this magnitude here becomes, when the magnitude of this voltage transfer function, okay, becomes 1 over square root of 2 without the high frequency gain, so we are just going to consider this part here, because this factor here, because at high frequencies we just have minus r2 over r1, right? So this factor here, it's basically the factor that reduces the magnitude of the voltage transfer function. So we need to decrease by 3 dB. So once this factor here becomes equals to 1 over square root of 2, we reach this minus 3 dB point here from our constant gain here at high frequencies. Okay, so we have to equate this one here, and one thing is that we can multiply uh, we can take the we can multiply that factor by j omega c r1. So let me make sure that we have that. So it's 1 over square root here, that's the magnitude, and okay, so let me first just to simplify our analysis, let's first take this. So this 1 over 1 plus 1 j omega cr1, and let's take this factor and multiply by j omega here and j omega there. So it's basically by multiplying by 1, and this means that we have j omega up here, j omega for the first one here, and then plus 1 over c r1. Okay, so that's the equation that we have. So we are just multiplying by j omega on the numerator and then denominator, and that's the equation that we get. Now we need to take this so we have to take this magnitude here and make it equals to the 1 over square root of 2. So 1 over square root of 2, that's the magnitude that would gives us the factor of minus 3 dB, and that should be equals to the magnitude. So the magnitude of j omega is just omega. Okay, and down here we have the square root of the real part, so it's 1 over cr1 squared, okay, plus the imaginary part squared, so omega squared. Okay, now if we square both sides of the equation, we get rid of the square roots, right? So let me just move this one here a little bit down. Okay, so let's keep with this one here. So it becomes 1 over 2 equals to omega squared divided by 1 over c r1 squared plus omega squared, right? So if we basically take these two up there, we get 2 omega squared, right? This 2 multiplies this omega here, and that's equals to 1 over cr1 squared plus omega squared. Now if we take this one here, put on the left hand side, we get 2 omega squared minus omega squared, so it gives us omega squared, just right here to save some space, omega squared equals to 1 over c r1 squared. And if we take the square root of both sides, so we get omega, and we can call it omega naught because that's a particular frequency of our system, that's equals to 1 over c r1. Okay, so it might be a little bit confusing the way I explain up here, but the thing is that we have this constant gain at high frequencies. If we decrease by 3 dB from this high frequency gain here, we reduce our gain by 1 over square root of 2. Okay, and why 1 over square root of 2? Because if we take the power, and power is proportional to voltage squared, so we basically decreased our output, the power at the output of this circuit by 50%. Okay, so that's why we get 1 over square root of 2, which means 3 dB. Okay, so if we take the magnitude, okay, the magnitude of this part here, which is just the factor that multiplies our constant high frequency gain, and equate that equals to 1 over square root of 2, the 3 dB. Okay, we can basically obtain, once we isolate the frequency here, we obtain this characteristic. Okay. Part D is that design the circuit for a high frequency input resistance of 1K and a high frequency gain of 40 dB and a 3 dB frequency of 2 kilohertz. Now, if we look at the high frequency input resistance, we know that for higher frequencies, this capacitor here becomes a short circuit, right? That's why it allows high frequencies to pass over this circuit here. And if it becomes a short circuit, we basically get the same circuit that we had for an inverting amplifier, right? And remember that for an inverting amplifier, the input resistance, okay, is just the voltage VI divided by the current, the input current. Now, because this terminal here is grounded, this one here is 0. So our VI minus 0 is equals to that I1 times R1. So if we isolate VI over I1, that's equals to R1. So if we want a high frequency input resistance, which is our R input, right, of 1K, it basically means that R1 should be equals to 1K. So that's our first component, R1 equals to 1K. Okay. Now, for B, a high frequency gain of 40 dB, it basically means that if we convert this dB here to an actual volt per volt gain, we get that 40 dB, okay, is equals to 20 log 10 of the gain, the voltage gain that we want. So the gain that we want is equals to 10 to the 40 divided by 20, which is 10 to the 2, which is 100 volt per volt. So that's the gain that we want. And we know that the high frequency gain equation, so the gain here is equals to R2 over R1. So from this equation we can calculate R2 now because we know R1 here and we know the gain, the voltage gain. So R2 is equals to the gain, 100 volts per volt times 1K ohm. So this gives us R2 equals to 100K ohm. So that's the second parameter. And now a 3 dB frequency of 2 kilohertz. So we know that a 2 dB frequency, a 3 dB frequency means that we must have that frequency equals to 1 over CR1. So now we can define the value of C. And that's basically, so if I write right here, so 2 pi f, that's omega, is equals to 1 over CR1. Okay, we can isolate C here. So C is equals to 1 over 2 pi f R1. And this gives us a capacitance, so if we substitute F as 2 kilohertz and R1 as 1K, right, we get 7.9.5 nanofarad, which is the third parameter for this circuit. And the last part, part E, is that when do we have the magnitude of the voltage transfer function equals to unity? So now we have to consider the entire voltage transfer function. And remember that the voltage transfer function AJ omega is equals to minus R2 over R1 J omega divided by J omega plus 1 over R1C. Okay, that's the entire voltage transfer function. So if we take the magnitude of that, okay, so if you take the magnitude, basically the magnitude of AJ omega is equals to the magnitude of this part here is R2 over R1 because it's just like real numbers times the magnitude of this one here, so it's omega squared divided by square root of this complex number here inside the parentheses, which is 1 over R1c squared plus the imaginary part, which is omega squared, and that should be equals to 1, right? So if we take the if we sorry, this is not squared because it's the imaginary part squared, so it's square root of this one here, so it's just omega, right? So if we take the squared of this left hand side in here to get rid of this square root here, we get that 1 is equals to R2 R1, and let me use it this way here, so they are both squared, times omega squared divided by omega squared plus 1 R1c squared. Okay, now if we isolate omega naught from these equations here, right, so if we take this denominator here and put it on the right hand side, basically expanding, we get that omega squared R1 squared plus R1 squared divided by R1 squared c squared should be equals to R2 squared omega squared. Now if we put this here on the left hand side and I group and basically isolate omega squared here and just simplify this equation here, we know that omega squared times R1 squared minus R2 squared is equals to 1 over c squared, which leads to omega equals to 1 over c squared times R1 squared minus R2 squared, and that's the frequency. Okay, now if we substitute the parameters that we just designed the circuit, so this C here is 79.5 nanofarad, R1 is 1K, and R2 is 100K, right? Let me just make sure. Yeah, so it's 100K. We get that omega is equals to 1 divided by 79.5 nanofarad squared divided by 1K. I think there's something wrong here. Oh yeah, so the way I isolated here should be minus C. Yeah, it should be minus C2 here. Or if we want to, we can just rearrange. So this is just to get rid of this. This should be R2 minus R1. In here it should be R2 minus R1. And of course this one it changes. I mean, if we take the negative for 1c squared, it should be the same thing, but just let's keep this way, which makes more sense. So this is 1k ohm, and here we have 100k squared minus 1k squared. and this gives us a frequency omega naught that is roughly 125.79 radians per second, which means that the frequency, which is equals to omega divided by 2 pi, equals to, or vary, 20.02 hertz, which is a frequency of roughly 20 hertz. Okay, so there's another way to verify this condition here, is that because we have a transfer function that decreases by 20 dB per decade, so if we want to return, and we know that we have a gain, so let me draw here. So this is the magnitude of the Bode plot, and we have, so let's say here we have 0 dB, and basically we know that very high frequency, the gain is 40 dB. Okay, and the slope of this curve here is minus 20 dB per decade, okay, or 20 dB per decade if you're going from, so it's increasing, right? So if you want to go from 40 dB to 0 dB, we have to go from, we have to decrease 2 decades, right? So 2 decades means basically dividing our frequency by 100. Okay, so our if we look at the design up here, one of the conditions is a 3 dB frequency of 2 kilohertz. So we can approximate this 3 dB here, which is something here, that's 2 kilohertz. So if we decrease by 2 decades, and 2 decades mean 1 decade we go from 2K to 200, and a second decade we go from 200 to 20 hertz. And if we decrease by 2 decades, we decrease by 40 dB, because we're going this direction, it's minus 20 dB per decade. So from 40 to 0, 2 decades, and then we get this frequency here, which indeed is very close to this analytical analysis here from the voltage transfer function, the magnitude of the voltage transfer function.